Well, it's my pleasure to give this lecture on stability and optimal control. And let me get straight to the point and define the optimal control problem I'm going to be discussing. We have a deterministic discrete time system where the state is xk, the control is uk. It's defined by a system equation. The state xk at time k is observed by a controller. Through feedback with a function mu k, it determines the control. And at each step, there's also a cost, g, that depends on state and control, and we assume that this cost is non-negative. Moreover, there is a destination state, some special state, which is cost-free and absorbing. Absorbing means that once you get to the destination state, you stay there. Cost-free means that you pay no cost while at the destination state. So given that the cost function is non-negative, roughly speaking, the essence of this problem is get close to the destination with small cost. Okay. Now, there are many applications of this problem. There are classical problems of regulation, regulating the state of the system around some set point, driving the state to some goal state, like in robotics, you want to do that. Also, shortest path problems fall in this framework, where you have a graph with a finite number of nodes, and you want to find a path to the destination that has minimum length, a very important, very classical problem. However, the state space here is arbitrary. It can be infinite. Usually, shortest path problems are defined over a finite state space. Okay, so to review more precisely, we have the system defined by the system function. xk, the state at time k, belongs to a state space x. The control uk depends to a control space u. And there's a certain control constraint that it should satisfy at each time. uk should belong to this capital U set that depends on xk. And now the state space and the control space are arbitrary. Finite, infinite, anything goes. We consider policies, which are sequences of feedback functions, functions of state to control that satisfy the constraint for every x. We have a non-negative cost function g, absorbing and cost-free destination t. And the objective is to minimize overall policies. This cost function, which is an infinite horizon cost, using g. So it's the infinite sum of the stage cost functions along trajectories, state trajectories and control trajectories determined by the policy pi. So to explain here, given an initial state x0, if you select a policy pi, then this determines completely the state trajectory for the future and also the control trajectory for the future, because this problem is deterministic. And at every step, there's this g cost incurred, and the sum over all these g's from 0 to infinity give you the cost of the policy starting at initial state x0. This is j pi of x0. It is a number, a non-negative number, or plus infinity. We allow the possibility that it's plus infinity. Okay, so the problem now is for a given initial state, find the best policy, one that, well, find the infimum of j pi, and if possible, find an optimal policy. And we call the optimal cost function j star. It's a function of the initial state. It is non-negative and could be infinite for some states. Okay, now let me turn to, a classical example, which I'm going to use later, is the linear quadratic regulator problem, where the destination is 0. We have a linear system involving matrices A and B, and we have a quadratic cost function involving a quadratic cost on the state determined by a matrix Q, which is positive semi-definite, and a quadratic cost on the control involving a matrix R, which is also positive semi-definite. So let me turn now to stability. Roughly speaking, a stable policy is one that drives the state to the destination either asymptotically or in a finite number of steps. It's a bit of a loose definition, and there are specializations of this definition in the literature. For example, this definition doesn't talk about how fast the convergence is, and doesn't say anything about the cost, how to compare different stable controllers. Now, stability was a hot subject a long time ago. When I first came to MIT, to this laboratory, about 1/3 of the research done in the laboratory was around stability-related topics. There are some famous faculty working here at that time, and it was really some very sophisticated research was taking place in the area of stability. Another hot subject in those times was optimal control, which was sort of an emerging subject at that time. And it's interesting that part of the motivation for research in optimal control was to be able to design stable controllers using the computational methodology of optimization. Now, there is a connection between stability and optimization, because if you look at an optimal policy, be able to find an optimal policy, and you look at the trajectories that are generated by this policy, then you can prove that J stars of xk goes to 0. So J star, the optimal value function, sort of acts like a Lyapunov function. It's not quite a Lyapunov function, but it looks like one, and with some further analysis, it could serve as a Lyapunov function and be used to obtain an optimal controller. On the other hand, it is not true that an optimal controller is stable in general. And this was a point that was made for example, in the famous 1960 paper by Kalman. It was a paper where he introduced controllability and observability. And in fact, part of Kalman's motivation for introducing controllability and observability was precisely to assert that the optimal regulator obtained from the linear quadratic problem was indeed stable. So he made a very close connection between optimization, stability, and the emerging concepts of controllability and observability. So let's leave this for now, and let's talk about infinite horizon dynamic programming for non-negative cost problems. Now, the classical research on this topic was done in the 60s, and the central result is that J star, the optimal cost function, is a solution of Bellman's equation. This is Bellman's equation. It's a functional equation for J star. There's one such equation for every state. We also require that J star at the destination is 0, as we know that it is 0. And basically, this equation expresses the principle of optimality in an infinite horizon context. It says that the optimal cost starting at state x can be obtained by minimizing overall controls, the sum of the first stage cost plus the cost to go starting from the next state. So it sort of makes sense. And the result is that J star solves this equation. However, this equation need not have a unique solution. It can have many solutions, an infinite number perhaps. J star, however, is the smallest non-negative solution. This is part of the theory. In other words, we have this J star. Every other solution of Bellman's equation lies uniformly above that. That's what this says. Another result here is that if you minimize in the right-hand side of Bellman's equation and obtain a mu stars of x minimizing point, and you piece together these values, then you obtain a stationary policy which is optimal. Okay? So minimization in Bellman's equation gives you an optimal policy if you can find the minimum. Another important piece of theory deals with the value iteration algorithm. It's a very important algorithm in infinite horizon dynamic programming, where you start from some function J0, and then you iterate with the Bellman equation operator, the dynamic programming operator. From J0, you get J1, then J2, and so on. You obtain a sequence of functions starting from the initial condition. But unfortunately, in the absence of additional assumptions, this algorithm is sort of erratic. You can show that it converges to J star if it is started from below J star, but even this requires some conditions. Now, when you start this algorithm from above, it can clearly get stuck because it will get stuck at any solution of Bellman's equations. I mentioned earlier that there are other solutions lying above J star, so if you start above J star, you may get stuck in one of those solutions. The policy iteration algorithm, which is the other major algorithm in dynamic programming, is also erratic. All sorts of strange things can happen with the policy iteration algorithm in general. These results hold even for stochastic problems, and there is no clear improvement for deterministic problems. Okay, so now let me illustrate this framework and the results in the context of a couple of examples. This is the simplest dynamic programming problem that you will ever see. It's a shortest path problem involving two states, state 1 and the destination state t. Now, at state 1, you have the choice between two controls. One control keeps the state at 1. So you cycle at 1. That's one possibility. The other possibility is to go straight to the destination. There's a zero cost for staying where you are, and there's a positive cost b to go to the destination. Okay, so now Bellman's equation is what you see here in red. It should be the minimum between b and j sub 1 here, okay? This should reflect the minimum between the action that goes to the destination and the action that stays at 1. Okay, what's the optimal cost here? Well, it is optimal to stay at 1 because this costs you nothing. So j stars of 1 is equal to 0. However, this optimal policy is not stable. It doesn't take you to the destination. Okay, it just keeps you at 1. And any policy that is stable, that terminates at the destination, has cost b. So the optimal cost over the stable policies is j plus, which is b, and it's different. Now, if you look at Bellman's equation, which should involve a minimum here, j star, which is 0, is of course a solution, and j plus also is a solution. And you can verify that any value in the interval between j star and j plus is also a solution of Bellman's equation. If you look at value iteration now, if it converges to something from, okay, the value iteration algorithm, if you start it from above j plus, then you can verify that it converges to j plus in one iteration. However, if you start it from below j plus, then you're going to be at a solution of Bellman's equation, so you're going to stay where you are, and so you're not going to converge to either j plus or j star. So that's one difficulty with the value iteration algorithm, and there's also a difficulty with a policy iteration algorithm that I'm not going to go into. Basically, it's possible to start with a suboptimal policy and stay at that suboptimal policy without making progress. Okay, so now here's another example from, this is a one-dimensional linear quadratic problem where the origin is the destination. You have a system that's linear and involves state xk, control uk, which are real numbers. However, the coefficient gamma is assumed to be greater than 1. So this system is unstable if left completely uncontrolled. Now, let the cost be equal to u squared. So this penalizes control, but does not penalize the state at all. Given this fact, it is optimal to just apply zero control and not care about what the state does. So the optimal cost is just J star X identically equal to 0, and the optimal policy is to use no control. But this policy is not stable because in the absence of control, this system is unstable and goes off to infinity, no matter where you started, unless you started at the destination. OK, so this is an example where optimal policy is not stable. And there is some analysis, classical analysis, that goes in this linear quadratic context. The Bellman equation for this problem gives rise to a Riccati equation. The Riccati equation is a quadratic equation in the scalar peak, which you see it here in red. And generally, the optimal cost function is quadratic with coefficient involving some p star, which is a solution of the Riccati equation. Now, in our case, p star is equal to 0, because the optimal policy is to apply no control. And indeed, we can verify that p star solves Bellman's equation. Now, you can try to solve this Riccati equation with a graphical argument, because this problem here is one-dimensional and p is a scalar. What we will do is plot the right-hand side of the Riccati equation, which is this curved red, this red curve, and try to make it equal to the left-hand side of Bellman's equation, which is this 45-degree line. At the point of interception of the two graphs, you obtain the solutions of the Riccati equation. And indeed, you see that p star equal to 0 is a solution. On the other hand, because this red curve is concave and is oriented like, you can verify that there's another solution. One more solution, this p hat. And this p hat can be calculated to be gamma squared minus 1. It's a positive number. Now, so we have the second solution, but what is the second solution? What does this correspond to? Well, it turns out that with a little analysis, you can verify that j hat is the optimal cost function over the stable controllers. Okay? So, so if you use a linear controller that stabilizes this system, it's going to have a cost function which is quadratic, involving a positive coefficient. And if you minimize over all stable controllers, then what you obtain is going to be this p hat. Okay? So this is also an interesting solution. It's sort of a minimum energy stable policy. Okay? That could be an interesting controller. You can also look at value iteration in this context. Now, value iteration can be defined in terms of iteration in the Riccati equation, iterating the Riccati equation. If you start at some initial p0, then from this diagram, you can verify that the generated sequence is obtained with this staircase graph. Okay? It's the geometry here of the graphs that I'm using. And for any initial condition, the Riccati equation converges to the top solution. Not the bottom solution, always to the top solution, except if you start with p star equal to 0. From every other initial condition, you converge to the p hat solution. OK. So now, if the problem here is that the optimal policy is unstable, this gives rise to a stabilization idea. Let's make it stable. And how can we do that? Well, we can add a little stability objective, this delta x squared to the cost function, which encourages the state to go towards 0. Then the problem is going to change. The optimal cost function is going to become j delta star, and it's going to be given again by the Riccati equation involving the scalar p delta star. And you can plot this p delta star in this figure, or you can do some calculation, and you can verify that as delta goes to 0, p delta star goes to p hat, not not P star, but P hat. So this idea of introducing a stability objective leads to the main idea of this lecture. Okay, so in summary, I'll give you first a summary of the ideas and the results. We add a small perturbation to the cost function in order to promote stability. In other words, we add to G a delta multiple of a forcing function P. This function is positive outside the destination and 0 at the destination, and sort of encourages the state to move towards the destination. Now, once you perturb the cost-to-go function, then the cost function of each policy is perturbed, and it involves the original cost objective plus a stability objective, which is the sum of the forcing function values along the corresponding trajectory multiplied with delta. And now for a given forcing function P, we say that a policy is P stable. Definition depends on P. Is P stable if this perturbed cost function is finite for all the relevant initial conditions, the one for which the optimal cost is also finite. Now, for a policy to be stable, two things have to happen. The original cost objective should be finite, and the stability objective should also be finite. Now, this sum of the p's being finite implies that p sub xk goes to 0. Okay? So this forcing function goes to 0, implying more or less that xk goes to t. So that's one role of P. It ensures that the P-stable policies drive xk to the destination. The second role of P is that it differentiates stable policies by speed of stability. In other words, not all P policies are the same. Some are faster than others. And how fast they converge to destination depends on the forcing function P. For example, P-stable policies with respect to the norm function are faster than P-stable policies using the quadratic function. And in fact, some policies may be stable, P-stable with respect to one function, but not P-stable with respect to the other. And this begs the question now, what is the fastest form of stable controller? Let's consider this case of the unit forcing function. P is equal to 1 for x different than t, and p equals 0. Now, this case is special. And what does it mean for a policy to be p-stable with respect to this unit forcing function? Well, for a stable policy, we have to have the sum of the p's being finite, which each p is equal to 1 if you're outside the destination. So the p-stable policies are the terminating policies, are the ones that reach exactly the destination in a finite number of steps for all initial conditions for which this is possible. Now, the terminating policies are the most stable. If you have a terminating policy, it is also p-stable for all possible forcing functions. Because for all forcing functions, for a terminating policy, this is a finite sum, which is finite. Yeah.
Are you taking delta fixed, or you're taking the limit of delta goes to 0?
Okay, the definition works for all delta. In other words, if it is p-stable for one delta, it is p-stable for all positive delta. Okay? Because basically, an alternative definition of p-stability is that both objectives, the original cost and the stability objectives, both of them are finite. And delta does not depend on delta. Okay. So this definition is independent of delta. It only depends, the stability depends only on P. Okay. Now, let's consider restricted optimality. Let's call J hat P the optimal cost over the P-stable policies. Okay? starting P, and of course it's a function of x. And for the most stable of the policies, the terminating policies, let's call J plus of x the optimal cost. And because J plus involves minimization over fewer policies, it is clearly bigger, okay? And if you plot in some kind of schematic way, if you plot J hat P, J plus, and J star, J plus majorizes all J hat P, which majorizes J star. So there's a hierarchy of cost functions, restricted optimal over stable policies, and also the overall optimal. And the important fact about this figure is that all of these functions are solutions of Bellman's equation. They solve Bellman's equation. Remember, Bellman's equation can have multiple solutions. And J star is a solution, but all of those are also solutions. Moreover, J plus, if it is finite, if there exists a terminating policy, is the largest solution. So J plus on one side and J plus on one side and J star on the other side delineate the region of all solutions of Bellman's equation. Now, there is a favorable case here. That's the one where J star is equal to J plus. Then Bellman's equation has a unique solution. In other words, if you can approximate the optimal cost with terminating policies, let's say epsilon optimal terminating policies for epsilon arbitrarily large, then you get J star equals J plus, and then J star is a unique solution of Bellman's equation. And moreover, there is a region of convergence result that I'm going to get to shortly. Value iteration converges from J star from any initial condition above J plus converges to J plus, and in the favorable case, it converges to J star from above. So things work out when the two coincide, J plus and J star. And let me refine this image a little bit for you. Okay, let's pick a forcing function P. And there corresponds a J hat of P, the restricted optimal function. And let's consider a set of functions WP, which are here at the top left. And these are the functions that lie above J hat of P and have values that converge to 0 for all P-stable policies. Now, this set WP can be viewed as the set of Lyapunov functions for these P-stable policies. They are driven to 0 using the P-stable policies. They're driven to 0 along trajectories generated by the P-stable policies. Now, for two different forcing functions P, let's say P and P prime, you will have, if J hat P and J hat P prime are different, then you're going to have a different set of Lyapunov functions. And an interesting result here is that from every one of those Lyapunov functions, if you start value iteration, then you converge to the corresponding restricted optimum. And for the special case of the terminating policies, the picture is like this. You get convergence of value iteration for every initial condition that lies above J hat. And moreover, this J hat coincides with a set of Lyapunov functions for the terminating policies. Now, in the favorable case, where J star is equal to J plus, we have convergence to J star from above, from every initial condition, and under some mild additional conditions, you have convergence from every non-negative initial condition. So this is the broad outline of the content of my talk. We try to make optimal policies be also stable. We can't guarantee that unless we introduce some kind of perturbation. Using perturbations gives rise to P-stable policies and a restricted optimization problem. And this restricted optimization problem connects with stability as well as solutions of the Riccati equation and algorithms for obtaining them through value iteration.
So in these P functions, the perturbation function that you're using, is it stationary? I mean, the function doesn't change with respect to time. So the
function P does not change with respect to time, but the P-stable policies could be non-stationary. Okay, that's important. It just doesn't work with stationary policies. Yeah. Okay, so all of this comes within the framework of abstract dynamic programming. I wrote a research monograph in 2013 on that, and I've been working on this subject since that time. There are updates to the monograph that are online. The research that I'm going to present today is very recent, and it's contained in 2 reports that are dated May 2017. You can find them on the internet. There are also other papers that were published earlier. This paper deals with the case, the favorable case, where J star is equal to J plus. The most significant paper is the one here that you see now, which is going to appear in SIAM Journal Control and Optimization. And there are other papers dealing with risk-sensitive problems, minimax problems, various special cases. And there's also a paper which is joint with Jenny Yu that appeared last year. It deals with stochastic shortest path problems. Okay, so now let me give you my outline. I'm going to first reiterate and clarify a little bit the definitions and the terminology that we're going to use. Then I'm going to give you the main results. Then I'm going to give you an example, which is an optimal stopping example, which makes clear the concept of stability. Then I'm going to say a few things about extension to stochastic shortest path problems. There are some extensions, but they are not very satisfying at the moment. The theory is not so complete for those. Finally, I'm going to try to explain how all this fits into the framework of abstract dynamic programming and also semi-contractive dynamic programming, which is a subfield within abstract dynamic programming. Semi-contractive refers to a situation where some policies are well-behaved, like being stable, and other policies not being well-behaved. And that's where the semi-contractive term, that's what it refers to. OK, so I'm going to repeat some of the things I said already. We have a system that's stationary, and its state belongs to an arbitrary set. The control also belongs to an arbitrary set, and it's constrained. There's a cost per state that's non-negative. There's a destination that is cost-free and absorbing. There are policies that are a sequence of functions that satisfy the constraint. And our objective is to minimize the infinite horizon costs along trajectories generated by policies. So now we consider adding a stability objective to the cost objective. We introduce this forcing function P, and we introduce the delta perturb problem for any delta that's positive. This is the same problem as the original, except that the cost per stage is G plus delta P. Now, the delta P term encourages the state to move towards 0 because of the nature of the forcing function. And we consider this composite or perturbed objective that involves both P and the original cost. And let's call J delta star the optimal cost function of the delta perturbed problem. Now, this delta perturbed problem is still an infinite horizon optimal control problem with non-negative cost, for which the classical theory applies. So J delta star solves the delta perturbed Bellman equation, which is the same as the original Bellman equation, but it involves the extra perturbation, the delta perturbation. And notice that this perturbed Bellman equation, if you take delta to go to 0, then you obtain the original Bellman equation. This is sort of a mathematical point of relevance here. OK. Now, we define p-stable policies for a given forcing function if the perturbed objective is finite for all x for which the optimal objective is finite. We define the restricted optimal cost over p-stable policies. And the interesting thing to note here is that in this perturbed problem, the p unstable policies are just ignored. They just play no role. The reason being that these p unstable policies, by definition, have infinite cost for some initial states. So they are neglected. If you do all the algorithmic optimization or the analytical optimization, they are neglected. And in particular, J star delta is equal to the optimal cost over the stable policies plus some perturbation that's due to the presence of delta. And that perturbation is finite. It's an O of delta and goes to 0 as delta goes to 0. So you have this first result, which is really pretty close to the surface. If you take the limit as delta goes to 0 of the delta perturbed optimal cost, then you obtain the cost that's optimal, but over the stable policies only, because the unstable policies are ignored in the delta perturbed problem. So this result can be used to approximate J hat P. We just approximate it by solving the delta perturbed problem, which is regularized. It's a little bit better behaved. And if delta is small, then we obtain an arbitrarily close approximation to the optimal stable cost. And here's another result that we're going to get into. The optimal stable cost, J hat P, solves the unperturbed Bellman equation. The reason is that J star delta solves the perturbed version of the Bellman equation. And if you use a limiting argument taking delta to go to 0, then you obtain that the limit of J star delta solves the limit of the perturbed Bellman equation. So, okay, it requires some mathematical argument to show that this is legitimate, but that's what happens here. Okay, so now let's go to terminating policies. These are the ones that correspond to the unit forcing function. Then they are the ones that reach the destination in a finite number of steps. And these are the most stable policies in the sense that they are stable with respect to every forcing function. We have this hierarchy of policies and restricted optimal cost functions. We have J star, the optimal cost function, the optimal p-stable cost, and the optimal cost for terminating policies. And all of these are demarcated by J star on one side and J plus on the other side. Okay, so now let me state precisely what you can prove. I'll start first with a favorable case where J star is equal to J plus. Then the result is that there exists a unique solution of Bellman's equation, which is just J star, and also, roughly speaking, value and policy iteration work well. Now, this favorable case occurs in the linear quadratic problem under the classical controllability and observability conditions. In the linear quadratic problem, the optimal policy is not terminating, but its cost can be approximated arbitrarily closely with a terminating policy under controllability and observability. What happens is that you can get close, arbitrarily close, with an optimal policy to 0, and then use controllability to construct a sequence of controls that takes you to the origin. So there does not exist an optimal terminating policy, but there exists an epsilon optimal terminating policy, which causes this J star to be equal to J plus. Now, for this kind of result to be true, of course, you have to have at least one terminating policy, okay? And that's where controllability comes in. Controllability means that there exists a terminating policy. And in order for this favorable case to occur, you have to have controllability. There must exist at least one terminating policy. And here's the result. Let's consider this class of functions which are non-negative and are 0 at the destination. The first result is that J star is a unique solution of Bellman's equation within this class. A sequence generated by value iteration starting from any J0 that is greater than J star converges to J star. And there's also a complementary result under an additional condition, compactness condition. For example, if the control space is finite, then you have convergence to J star from below. So you have convergence to J star from above by this result here, convergence from J star to J star from below by the classical results under this compactness condition. So you have convergence from every initial condition. There's also a policy iteration result that's available for this favorable case, and there's also another result that relates to a variant of policy iteration, so-called optimistic policy iteration, but let me not get into this. So these are the results for the favorable case. The more complicated case is when J star is different than J plus, in which case we have a distance between, there's a space between J star and J plus, and the space demarcated by these two ends is where all the optimal stable cost functions lie. And here, whenever I talk about J hat P, I'm implicitly assuming that J hat P is finite for all the relevant x. Without this assumption, J hat P goes off the charts, goes to, has infinite values, and this picture does not hold. And however, this is true if there exists a P stable policy, or even if there exists, if there exists at least one P stable policy. And here's the result. This is the more recent result. Let's consider the set of functions P. For a given P, let's consider the set of functions P that lie above the optimal stable cost, and their values are driven to 0 along the trajectories generated from P stable policies, from initial conditions that are relevant. Now, this W hat P can be interpreted as the set of Lyapunov functions for the P stable policies. They're the functions that are driven to 0 along the trajectory of the trajectories of these P stable policies. Okay, and now the result says that J hat P is the unique solution of Bellman's equation within this set of Lyapunov functions. J plus, the corresponding result for the terminating policies, is that J plus is the unique solution of Bellman's equation within this set. Now, because J plus is the maximal solution of Bellman's equation, the corresponding set W takes this form here. So we have uniqueness of solution within this set. And moreover, any sequence generated by value iteration starting from a Lyapunov function of a given P converges to J hat P. There are also versions of policy iteration that converge to J hat P that are a little bit more complicated than the usual, and let me not get into that. Okay, so now let me look at an example. Yeah?
In this case, is it, earlier you showed example where you have P functions such as the quadratic norm, for example, or in principle I could choose any alpha norm, unnormalized of course,
Yeah, this is an example where you have an infinity of forcing functions giving rise to an infinity of set of stable policies.
When J star is not equals to J plus, are there conditions under which you can choose sequence of P's, P functions such that J hat P goes to J plus?
I haven't looked at this idea, perhaps. Here, the forcing function is stationary.
If you think of function x to power alpha, where alpha goes to 0, then
Yeah.
really you are trying to approximate the step function.
Perhaps I haven't thought about that. It may be interesting to look into. Okay, so this is an optimal stopping problem where I did state there are two actions. Either stop and go to the destination directly and pay a stopping cost, or continue and stay at a non-destination state. Now, okay, so here the state space is Rn, and the destination is the origin. So we're trying to go to the origin at minimum cost. And at a non-destination state, we have two choices: to stop. This is the black move from x at the top here. It costs you a constant c, and you move to 0. The second choice is to continue, in which case you move to the state gamma x. You move closer to the destination. Gamma is less than 1. You move closer to the destination, but not quite there. Okay? So the policy that continues everywhere just takes you down towards the origin, but never reaches it, okay? Asymptotically converges at the rate of a geometric progression, asymptotically converges to 0. Whereas the stopping cost goes there directly. Now, you can guess what the optimal policy is here. If you're far, far away from the destination, then you don't want to continue and pay this absolute value cost forever, and you're going to, it's better to just stop. However, if you're close to the destination, then the stopping cost may be large relative to the cost that you will pay for continuing asymptotically to the destination. So in this particular figure, in this particular example, the optimal policy is to stop outside the circle that you see there, which has radius 1 minus gamma c, and to continue where you're inside the circle. Okay? So if you're far away, you go directly to the destination. If you're close, you just go gradually to it, and it's better to do it that way. Bellman's equation takes this form. It reflects minimization over the two actions, stopping and continuing. Okay? And let's make some observations here. First of all policies are stable. They're just stable for different p, because they all lead you to the destination. Whether you stop or continue, you stop at some point, or whether you continue, you're going to get to the destination either asymptotically or in a finite number of steps. Let's look at Bellman's equation and what are the solutions. Okay, the optimal cost function, you can solve this equation fairly easily. It's the minimum between these two expressions. Okay, and it characterizes the optimal policy as I have described. If you are within 1 minus gamma c of the destination, then this action is better, and you continue. Otherwise, you stop. On the other hand, j plus, the function that's identically equal to c, that corresponds to the policy that stops everywhere, is also a solution of Bellman's equation. Okay? If you plug in here j hat equal to c, you will see that it's a solution of Bellman's equation, right? So we have two solutions, the extreme solutions, the minimal and the maximal solution of Bellman's equation. But in between them, there's an infinity of solutions. To obtain some solutions like that, take any cone, okay, this green cone that you see here, take any cone and make j to be equal to j star within this cone, okay? And take j to be j plus in the complementary cone. That's also a solution of Bellman's equation. And it gives rise to different p-stable policies. So let me now specialize this example for the case of the real line, where n is equal to 1. Now, there are exactly 4 solutions of Bellman's equation in this case. One is J star, which is given by the figure on the left. It is the stopping cost outside a certain radius and the continuing cost inside. So it looks like this. J plus, on the other hand, is the constant C function, corresponds to stopping from everywhere. And there are 2 more solutions. One is this one in the middle, and there's also a symmetric version of that. Now here, this corresponds to policies, to optimization over policies that move from the left, move directly to the destination, and from the right, move asymptotically using the continuation policy. And these 4 Bellman equations correspond to different forcing functions. Any positive multiple of these Bellman equation solution gives you a forcing function and corresponding sets of p-stable policies. The p-stable policies here are the ones that like optimal, they converge to, they use the continuing cost when you're close to 0. For this case, the p-stable policies are the ones that stop eventually from the left but continue from the right, and the others are the ones that stop from every initial condition. And there's a corresponding regions of convergence result. Starting from different type of initial conditions, you get convergence to different solutions of Bellman's equation. And the forcing functions here are the ones that are continuous at 0 on the left, are greater than constant on the right, and constant on the left, and right continuous at 0. So there are only 4 solutions here. For dimensions greater than 2, there's an infinity of regions of convergence, an infinity of solutions of Bellman's equation, an infinity of Lyapunov functions tailored to particular stable policies. And it's a simple example that sort of conveys all the complexities that can occur in this framework. Okay, so I think we're getting close to the end, so I'm going to rush this a little bit. There are some extensions of this theory to stochastic shortest path problems, which involve systems with a stochastic disturbance W. Bellman's equation takes this form. There's a long history to this problem for the finite state case. John Tsitsiklis and I did some work in 1991, which revolves around the notion of a proper policy. A proper policy is one that leads to the destination with probability 1 from every initial state. And this is sort of the analog of a terminating policy. There's also an extension of this result, which addresses the case where J star is different than J plus. And there's also an extension of this result for the case where you have infinite state space and non-negative cost. Then you need an extension of the notion of a proper policy. It's one that's bounded. It's the one that corresponds to whose cost function is bounded, and also reaches the destination in a bounded expected number of steps, bounded over the initial condition. And there are analogous results. This is not very satisfactory because the definition of a proper policy assumes that J pi is bounded. And that's, in many applications, this is not satisfied. Okay, just a few things about abstract dynamic programming. I looked into Wikipedia, the source of all wisdom these days, and it gives this nice definition of abstraction in mathematics. It says that abstraction is a process of extracting the underlying essence of a mathematical concept. removing any dependence on real-world objects, no applications, no regard to applications. And generalizing so that it has wider applications or connects with other similar phenomena. And it also gives the advantages of abstraction. It reveals deep connections between different areas of mathematics. Areas of mathematics that share a structure are likely to give different, similar results. Known results in one area can suggest conjectures in a related area. Techniques and methods from one area can be applied to prove results in a related area. All of this can be summarized in what I've written here. Just eliminate all the clutter and look at the fundamentals as they stand out with the clutter removed. Now the question is, what is fundamental in dynamic programming? And it's fairly easy to conclude that what's fundamental is the Bellman equation operator. So instead of having a Bellman equation operator for deterministic problems, for stochastic problems, for minimax problems, and so on, we introduce a general type of Bellman operator in terms of an abstract mapping, H, which depends on state, control, and the cost function J, and the Bellman's equation for the optimal cost is what you see here. For the deterministic optimal control problem of this lecture, it has this form. For a stochastic optimal control problem, discounted or undiscounted, H takes this form. And there are other examples that fit this abstract framework: minimax control, semi-Markov problems, exponential risk-sensitive cost, and others. And the key premise is that H is the mathematical signature of the problem. If you know H, you know an awful lot about the problem. Because depending on the properties of H, whether it is monotone, whether it's a contraction, sort of similar results hold. So abstract dynamic programming uses a top-down development. Starting from H, you develop analysis and methods in the abstract, and then specialize them to particular types of problems. Okay, semicontractive is a particular branch of abstract dynamic programming where some policies are well-behaved and some are not. For example, a well-behaved policy in some context might be a policy mu, such as this mapping is a contraction mapping in J, this H of x, mus of x, and J. A stable policy is an example. A proper policy in the context of stochastic shortest path is an example. Generally, if you have policies that are not well behaved, they cause problems. Multiple solutions of Bellman's equation, lack of convergence of the basic algorithms, and that's the essence of this semi-contractive model. So there's more here. We introduce a class of well-behaved policies, and there's a formal mathematical definition for that, definition of regularity. We define a restricted optimization problem. We show that the restricted problem has nice theoretical and algorithmic results. And then we have favorable cases and unfavorable cases, as in this example that I have described. So here's my last slide. The highlights of the results are basically a connection between stability and optimization through the idea of a forcing function, perturbed optimization, p-stable policies. There's a connection between solutions of Bellman's equation, Lyapunov functions, regions of convergence corresponding to different types of stable policies. And there are value and policy iteration algorithms for computing, in principle, the restricted optimum over the p-stable policies. Now, there are some outstanding issues. I'm going to mention just one. How do we compute an optimal p-stable policy in practice for a continuous state problem? If you have a continuous state problem, you have to discretize in order to solve it analytically. But this may obliterate completely the structure of the solutions of Bellman equation. Some solutions may disappear, some other solutions may appear, and there are some questions around that. A special case of this is how do you check the existence of a terminating policy which is the same as asking the question, how do you check controllability of a given system? Algorithmically, how do you check that? And there is also some strange problems that involve positive and negative cost per stage, where J star may not even be a solution of Bellman's equation. And some extensions to those are an interesting direction to look into. So that's it.
Maybe we take just one question or two and move upstairs to the reception.
Yes.
So uniqueness throughout the discussion was seen for non-negative solutions. I assume for the Riccati equation, for the Bellman equation.
Yes, within this, when we talk about uniqueness of solution of Bellman's equation, we mean uniqueness within non-negative solutions that are possibly extended real value, that could take the value infinity.
So could this be extended for the negative solutions, like anti-stabilizing solutions? Can we have the homotopic argument as well in that sense?
Non-negativity of the cost function is an important assumption here. A lot of the mathematics depend on non-negativity. And if you notice the last bullet that I rushed, if you consider problems with both negative and positive costs per stage, then all sorts of strange things can happen, including the fact that J star may not satisfy Bellman's equation, which is really an unusual phenomenon. So some major extension and major overhaul of this analysis has to be done before it applies to problems with both positive and negative costs.
Well, thank you, Dimitri.